Okay, thank you very much. So as Georg just mentioned, if someone of you know me, will know me from my time in Jülich, at the Jülich Supercomputing Centre mostly. Since about 1 month ago, I'm working in a sabbatical at SiPearl because I always wanted to see how processors are actually built in real life, in industry. So especially processors for HPC, that is the field that I am in. And therefore, this presentation is a little bit of a mixture of work we've been doing from the Jülich side in cooperation with SiPearl. I also worked on by SiPearl themselves with contributions from a bunch of people that you see here acknowledged on the first slide. So my idea is so I'm just new to the company, so I'm learning a little bit how it works inside and trying to present you what I've learned until now on how processors are being built. So I will basically just start with the motivation, why at all doing like this in Europe, which kind of chip should we build, what are the performance trends that we see, and then what it means developing a CPU for production. Then I have some material on co-design we've been doing using the M5 from the team at Jülich and within the European Processor Initiative. And then with come to the Rhea, to the architecture of the first CPU developed by SiPearl, and then lessons learned. So why do we actually want, and we think it's important to build such a chip in Europe? So if you look into the supercomputing industry from the EU perspective, you realize that about 1/3 of the facilities of the consumers of HPC resources are in Europe, but there's only about 1/20 of the equipment that is provided by Europe, and it's actually 0% of the processing units that are being developed in Europe. You might say, wait, why is this a problem? So the problem is that if we don't have homegrown technology, at some point we become something like a digital colony. So we need to have this expertise. And I know that people here in Erlangen have been working from the academic side for many years developing processors. But I think it's also important to have products out there you can then employ in our HPC systems. So with this reasoning, around 2018, the European Euro HPC joint undertaking started. And this is a kind of association where the European Commission and many countries in Europe join together efforts and funding to both deploy HPC systems and also develop technologies, both hardware and software for those systems. And very soon afterwards, this European Processor Initiative, this European funded project started with all the partners you see there on the right. The coordination is taken by Eviden, and then there are many other partners, industrial and academic partners that are involved in two lines of development. So on the one hand side is an ARM-based CPU, and on the other side, a RISC-V-based accelerator, actually several accelerators. What was clear within the project is that if this shall become a product, something you can put into the market and sell and productize, there needs to be a company that drives it. And that's where the idea of SiPearl actually came from. It was rounded from within the European Processor Initiative. But before going there, so the first question is, which kind of chip do you want to build in Europe? And there are, of course, several options. So you could, first of all, you need to decide how to do it. So what kind of market you want to address and which is the time horizon in which this has to be done. The first target was decided to be HPC. So as I said, this comes from the Euro HPC Joint Initiative, the original funding source. Of course, also AI. Let's say 4 years ago, AI was not such a big topic, but now it is definitely. And the idea was to have something like within a 5 years time range, have something on the hand you can then put in a computer, which is very, very, very ambitious if you're speaking about a real full-fledged CPU for HPC. Which kind of device then? One could decide to build a GPU, but then there's a question, can you actually compete starting from a startup, from a small company with the dominating company in the market, which is NVIDIA, now a little bit also AMD. Furthermore, all the designs are closed source. There are no licensable solutions for GPUs. You can then go for a CPU where there are various providers for ISAs. The software is also well established and there is a wider market out there. But you could think about building some specific accelerators, for example, an AI accelerator. But there, although there are several options in the market, also they are not licensable, and you would start from scratch, both on the hardware and on the software development. So the decision was then taken very early in this context to go first for a CPU. which kind of opened, first of all, for HPC, but also for the wider server markets and opportunities relying on software solutions and licenses that are available. Then, which is the instruction set architecture? So you have the three main alternatives. There are some others out there, but these are the three major ones. x86, perfectly established, very mature, but not licensable. So you cannot go and buy it from a license from Intel, at least not easily. ARM, there is also a major software stack. You have a growing market, or they are growing on the server market, and they have licensable solutions, so you can license this from ARM. And the other option would be RISC-V. So when there is open ISA, where you can develop your own design based on the standard set by the RISC-V Foundation. The problem here is that given the time frame that was set as a target, you do not have yet there the software support for the server and HPC market that you would require. So the decision here was to let's go first for ARM. RISC-V, we start with the accelerator side in the European Processor Initiative, and at some point we can hopefully then jump and continue with the development on the RISC-V side when there is more software environment out there. And then what kind of chip design based on this ISA? Well, you look into the competition and you try to identify what are opportunities for uniqueness. So it's clear you cannot go head-front competition with Intel or AMD, but you can think about what are the areas where maybe in HPC in particular, there is a use case, there are a specific kind of corner case that is not well covered by the technology out there. Yeah, and then for identifying such a niche or such a uniqueness, the first thing you need to do is look into the state of the art and see where there are any gaps. So if you look into the performance trends, you all know this very well. So we had monocore architectures until around mid of the 2000s, 2004 or so, with then the scaling, or if you want, the frequency wall started to pose serious problems. Then we moved into the many core architectures. And at some point around the 2010s, one realizes even going many core, if you want to deploy at some point exascale, this is just consuming too much power. So you need to go for heterogeneous architectures. And we started to have mostly GPUs integrated in our systems. The question is where we are now. So we still, if you look into the large scale machines, there are tons of GPUs out there. We are entering now in this, what you can call this the reticule size wall, if you want, the end of Moore's law, where new concepts are coming up, looking into this aggregated system of chip designs that hopefully bring more flexibility and performance scalability. So that's how evolution went. Of course, always looking for more performance at an affordable price, and especially at an affordable energy price. Certainly, this has brought more performance, and that's the typical plot you see in many, many presentations with the statistics from the top 500 list over the years, how the performance has been growing exponentially. And you see in blue, this is the peak for the top number one, the number one on the top 500 list, and on green it's the median value for the top 10 systems, and then you have the peak and the maximum value for HPL. So it's nicely growing, and if you look into kind of the accelerator era around 2010, 10, 11, 12, it still continues growing, and it's clear that GPUs in particular have brought a significant performance gains. But now you see also that the lines are kind of flattening, even if you look only about the peak performance of this particular benchmark. The question is, how does it look in terms of efficiency? So one thing is the peak performance. The other thing, the peak performance of the hardware, how close do you get when you run an application to this peak performance? Even HPL, which is actually quite small and easy to adapt compared to other applications to the hardware, you see that there are efficiencies that go between 40-50% up to 80%, not much higher than that. You see, interestingly, when you look into the top one, the Fugaku system, the ARM-based CPU from Fujitsu came up, how there the efficiency is higher than for the rest because they have high bandwidth memory on the CPU. But in general, the efficiency, even for this benchmark, which is where you can easily get to the peak performance, is not really improving. It's kind of oscillating a lot depending on what comes up. If you look for another benchmark, a little bit more representative that also takes into account the memories of system and the interconnect on the chips, you see on the left the values for the number one and the top 10 in the performance, and you see on the right the efficiency. That's the same kind of calculation, performance measured by HPCE with respect to the peak performance of the hardware. So here it grows a little bit, but if you look into the top one, it's also a little bit flattening. Efficiency, we are looking at values of around 1 to 2% efficiency for this particular benchmark, which is not very. And also here you see even more strongly how it is different, how it growth with Fugaku with this CPU based or CPU which high bandwidth memory. If you compare both HPL and HPCE, you see for the number one system, the gap that varies over time. If you look at the top 10 median average, the gap seems to be increasing. So on a performance gap of 14% to 80% in the latest system. The message of what you realize is that the peak performance you measure with HPL will not translate into the peak performance of other applications. And the efficiency is a key question one needs to look into. Efficiency has to do, in this case, with the ratio between byte and flop performance. So how much data can you transfer between your memory and your processing unit with respect to how many operations you are doing during the time this is being transferred. And this is decreasing drastically over time. So you can say actually from the time when we started to have these many core, multi-core CPUs, then this curve has gone very close to the zero axis. And I know you don't see that much there. So therefore, I decided to also do this in logarithmic scale. And this is exactly the same data. So you see where the points land and the typical values here are around 0.1. What means 0.1 means that if you are doing the same amount of data movement as operations, 10%, you will have a 10% efficiency. So you will have 90% of the time you will be just waiting for data to come. So it's not good news if your applications are memory bound, and most of the applications we have in HPC are memory bound. So that's kind of the niche or the kind of the position where in the definition of the CPU at SiPearl, they decided to try to put an alternative there. So to have a CPU that provides really high byte per flop performance, in particular for the HPC market. That's the target, and that's the result of this analysis. What does it mean developing then a CPU in the company? So first of all, there are many steps you need to do. First of all, you have to set up the company. You have to find the right people to work in this company. You need to set up the whole infrastructure with their data center and everything else around it. You have to get many million euros funding to support it. You need to then design the chip, to produce the chip, and to find customers to install it. And funny enough, you have to do all of this at the same time. In Europe, where at that point nobody was doing this in this context, or let's say with this kind of target. The company itself, so addressing the first items on this list, this is a private company to produce this European CPU. It was founded in June 2019. Is, as I said, part of this context of the European Processor Initiative. The original seed funding came from the European Union through the European funded project, this EPI. But of course, lots of additional funding had to be acquired through investments. And you see here some of the logos of the companies and institutions that are part of the investment of the company. One of them is, for example, ARM, and also the design, as I said before, is relying on the ARM architecture for the reasons mentioned also earlier. So because you have a software stack that is established, and you can concentrate and focus on the chip development first. There are also partnerships with the different companies. So AMD, Intel, NVIDIA, they produce GPUs that can be coupled to the CPU from SiPearl. That's the role of these partnerships, making sure that there is a good communication between the different components. And of course, you also have the typical partnerships with the integrators, with Eviden, HAP, and so on, so that they can have bits out there for this kind, so with systems with this technology. Customers, the first target is Euro HPC, or let's say the European HPC systems, with the hope that, of course, when things are established and running, you can also compete worldwide. But I mean, it's a SME that has grown very quickly. There are by now over 200 employees that come from some of these companies mentioned there. So from Atos, from Intel, from Infineon, and others. People that have been for many years working on the chip development in different areas. be it embedded, be it also for networks or for other things. And the company is really set up in a European level. So the headquarters are in Paris. This is in France, in the near Paris. It's called Maison Lafitte, with other 3 sites in France, Grenoble, which is the one here. Then we have Sophia Antipolis and Massy, which is in the south of Paris. But there are also sites in Germany, in Duisburg, where, for example, I am associated, Spain, in Barcelona, and a new one in Bologna. The idea is there are not many people with this expertise out there, with the kind of expertise that is required. And instead of expecting that everybody will suddenly move to Paris because they don't have families and anything to deal with, let's try to build up offices where you have teams that have this expertise and you can have them on site on the places where they are located. To my experience, at least, as a unique kind of settling for a new company on a business which is extremely competitive and extremely difficult to establish in concurrence with others. But this is kind of the more, let's say, industry management side of things. The question is, how does the technical side look like? So how is the chip design, the design steps done? And I think that many of you maybe are aware of these things, but I was not sure the audience here what are the different backgrounds. So I try to do this a little bit also starting from the basics. There are many different steps to develop a CPU. Of course, you always start with the chip specifications, with the requirements and defining the microarchitecture, including like power, speed, and the targets you want to have for the CPU. And you need at least 2 teams, the design team that generates this RTL, this register language, I have it here, register transfer level, right? So many acronyms in this business. And then the verification team that then generates the test bench for verifying what the others are producing. Next step is you do kind of the chip partitioning. So you know what are your design targets. You need to identify what are the functional blocks that need to work together to deliver these targets. And these are so-called IP blocks, intellectual property blocks. So you need to decide what is existing already out there that delivers the functionality for this block that I can just license and use? For example, the ARM core. What are others that I need to develop from scratch to make sure that I meet my targets? The more you do on your own, the more differentiated your design is, but also the more risky it becomes, because you start developing things from scratch that have not been developed or tested anywhere else. At the end, you end up doing a mixture of things on your own and things then licensed. Then the next step is design entry or functional verification, where you confirm that the functionality that you put into these building blocks is really delivered by the IP blocks you have selected, and you start generating this RTL, which is basically the language that defines and designs the hardware. You need functional simulation tools to verify the logical behavior. You need also timing simulation tools to make sure that the timing requirements are met. Then you go into the block synthesis. So it's about generating the kind of hardware-defining code, translating then this RTL code into gate-level netlist and creating then a synthesized database. Then you go to the design for tests, or DFT. So there are DFT teams in the company that are responsible for making all possible tests of the design, testing the registers, testing the memory built-in system, and so on. The next step is floor planning. So you have your functional blocks, you know what you want to do with each one of them, but you have to define where exactly in the silicon are they be located. And this decision, you try to do this, of course, so that you minimize the chip area, because then you maximize your yield at the end, that you facilitate the routing of the signals through the design, and that you improve also any possible signal delays. And then the next step is the clock tree synthesis. So building the clock tree and making sure that the timing is met so that the signals go properly through the circuit and there are no additional delays being integrated anywhere. Step number 8, this is becoming a bit lengthy, sorry. So place and routing, so optimizing the signal delays over the wires. Then the final physical verification and timing with, again, lots of acronyms that basically check that the geometry at the end fulfills what you had originally set as targets, and it's also fulfilling the requirements from the foundry where you are doing the tape out. At the end of these steps, you are generating then a so-called GDS file. That is the file that is used for tape-out by the foundry. They also do their own checks afterwards and so on. But that's what you send them to tape-out to produce the chip itself. So all these steps, they are more or less done in as far as possible. Some things can be parallelized, but in general in a sequential manner. And if you find a problem somewhere down the line, that means you have to redecide to adapt something. You fall back to some of the steps before, and you have to go again through all of them. So it's very complex. It's very time consuming. It also requires lots of different complementary expertise from a wide team distributed, in this case of this company, across Europe. So some of the steps I mentioned also simulation tools that are used, and there are lots of simulation and emulation tools that are necessary. None of them is perfect, so each one of those tools is defined and is designed for a specific purpose. If you want to be very accurate, you go very down here the stack to something like FPGA emulation. If you want to be very fast on your simulations, then just get up on the upper layers of the stack somewhere with trace-based models or fast models. And somewhere down the middle, and one can argue that there are different, you could classify these things in different orders, but in general, the lower part should be cycle accurate, the upper part is more loosely timed. In the European Processor Initiative, in this project, GEM5 has played a very important role because GEM5 is accessible for also academic institutions. It's open source and it offers its very flexible environment to simulate things like a chip architecture. And that's what I want to show you in the next slide, the kind of co-design we've been doing using GEM5 in EPI. Maybe first I should say what I mean by co-design, because everybody understands or seems to understand different things. To me, co-design is looking into the interaction between the application code, the software stack, the hardware devices, and the overall system architecture to find out the configuration and the decisions you need to do in each of these 4 steps to achieve at the end the best performance and energy efficiency. In the context of EPI and in the context of SiPearl, we focused on this diagonal here, on the interaction between application code and hardware devices. We didn't look much into the software side. We didn't look much into the system architecture because these are things that come a bit later down the line. And in application code, the work that the Jülich team has been doing has been mostly based on benchmarks and kernels of applications, because GEM5, I mean, you cannot run just a full-fledged Romax application or something. It would take an eternity. For this Rhea 1, which is the first CPU developed by SiPearl, the focus is, as I said, on chip-level microarchitecture. So the activities that the project had were on chip design, emulation, and tape-out. That's the part that SiPearl take care, mostly. Then there is low-level software, development of compilers and so on, with many partners involved. And then simulation modeling and benchmarking, that is the task that, for example, Jülich has been involved in. There were, during the project, a selection of around 16 partners was involved in this last part, in simulation modeling and benchmarking, with in total over 40 codes involved that contain benchmarks, mini applications, and kernels in a variety of scientific fields. And these are the fields that we had, are over 40 different codes. Biophysics, biology, material science, CFD, deep learning, you name it. So many of them. And the usual suspects in terms of reference benchmarks, HPL, HPCE, Stream, DGEM, Mini-FE, and these kind of things. Also Wolverla, which I think comes from here, was part of the studies. If you are interested and you want to have a look, there is here a link to the repository, which is open source. You can have an access and have a look at the codes that have been used. The process itself, we had some hardware platforms. In the case of ARM, because the chip is under development, the ARM reference platforms we were using were either A64FX from Fujitsu. This is similar well, at least it's also the same ISA, and things like SIMD and SVE, the scalable vector extensions, are supported. We also had Graviton 3 chips that are also these ARM Neoverse. And then from the RISC-V side, they had several software development vehicles based on FPGAs and also based on different kinds of emulation systems. Validation and co-design. Validation, what I mean in this context is running applications and testing how competitive is the behavior, the performance result with respect to other platforms, looking into vectorization levels and things like that. And co-design, in this case, I mean the going into the simulation of the hardware architecture and trying to extrapolate, playing with the parameters, with the design parameters, trying to identify how do they impact the performance of applications. What we learned on the side of the validation and co-design partners was then fed for the architects of the CPU, of the Rhea CPU, and of the accelerator, the RISC-V accelerator EPAC, so that they can implement it in future chips. This, I think I should say explicitly, the development cycles of these things are very fast. So the design of the current generation is most of the times already settled, and whatever you feed in as co-design will then have an impact, if at all, in the next generation or the one afterwards. So there is some time for the development teams to absorb the feedback that they receive. And this is something one has to keep in mind. The M5 simulator, again, I guess many of you know this. I put here, this is a picture and a reference from the original paper from Lowe Power. This is a cycle-level computer architecture simulator that is event-driven and object-oriented. So the idea is you have several different models, for example, several CPU models. You have also several DRAM devices or memory devices. You can also have several network-on-chip implementations. And these things, you can couple them together as if it would be a Lego to simulate a specific chip design. There's also cache coherency with different models and so on. It's a very powerful tool. It's very flexible. You can do many things. But because you are plug and play in different components developed by different people, it can happen. You have to be very careful that whatever you do is repeatable. So when you do different experiments, that the results are repeatable, they're reproducible. And if you find errors, it takes an effort to debug things because you need to first identify from which one of those modules does the problem come from. Yeah, and then the idea is you have on the one hand side a description of the hardware with a given core and cache hierarchy and memory. Then you have the configuration of the simulation that is normally a Python file. You run this through the M5 simulation environment and you get on the one hand side whatever the application generates, but you also get lots of counters for cache misses, cache hits, prefetch units, whatever. I mean, you have lots of statistics you can collect here. There has been quite a work in the project to extend GEM5 to adapt it to the needs of the project. So key features that were kept in mind when thinking about extensions to GEM5 was, first of all, kind of a set of Python scripts, so a Python-based script environment that addressed, try to achieve better reproducibility and also better model configuration. So instead of having to go and rewrite yourself all these Python codes every time you want to change a parameter into the configuration, there was a framework to automatically generate this based on a given YAML input file. That's what they said here. So at the end, an EPI GEM5 benchmark is defined by 4 components. You have one, the first one is the Linux system image. Then you have the base architecture configuration that you provide as a YAML file and automatically generates the Python files that are needed for GEM5. Then you have a base computational workload, binary from a benchmark, and you give them architecture parameters space. So which are the sizes of the caches you want to play with? What are the memory latencies or network latencies you want to play with? Also, this is all open source. It's here, it's the link if someone is interested. So the whole Python environment is published. What is not published within this, to be fair, is the specific configuration of the chip that is owned by, in this case, SiPearl or some other company. Yeah, this is just to visualize it. So on the left, you see the semantic configuration of the simulation. You can define in this kind of file the number of CPUs, the number of vector units or the length of the vector units, the cache sizes, and so on. And on the other hand, you have the definition of the benchmark with different ranges of parameters you want to be checked in a given simulation run. So these two things then come together to generate the simulation results. And there are also actually Python files for the calculating or producing the plots and the visualization required to extract real insights from all this information. Features that have been added to GEM5, taking into account the requirements of the project. So the requirement, one of them was being able to model the cache hierarchy and the network traffic. And for this, Garnet support for AMBA-Chi, which is the cache coherency protocol from ARM, has been implemented. It was necessary also to reach the bandwidth performances of these modern ARM mesh networks. And for this, the multiple links carrying the same virtual networks were implemented in the model. We wanted to simulate different NUMA topologies, and also for these NUMA domain identifiers were added to the GEM5 model. There was also support necessary to support the ARM CPU caches, and also extensions were done there, and in general achieve the CPU performance from ARM. For this, there has been improvements on the model front end. There has been also validation comparing with available Neoverse devices like in Graviton. This is one base architecture represented on GEM5. You see here on the right the representation of one quadrant. These are routers, the gray boxes are routers, and then you have the connection here to the cores and to the system level caches that is distributed in slices across the system. So in this particular configuration, we played with different ones. So the one I will show you that was used for the generation of the next results on the next slide is this one. So these are 16-core, 64-bit ARM Neoverse P1 with two SVE units. We played with different vector lengths to see what is the right size to be taken. Cache sizes, SLCs, network on chip is this Garnet AMBA-Chi protocol, and then memory with high bandwidth memory, 8 channels, 2 times 8 GB. Why it's important to simulate all of these things? Because you try to be as accurate as possible. One thing is what you design on RTL and on many of these things. You want to have a high bandwidth at the end visible for your application, but you cannot always calculate this just on the paper. So you need to simulate very carefully the architecture to make sure this is reachable. And then I give you just, I think it's 4 examples of different studies that we did, or that the colleagues in the team in Jülich did with GEM5. The first one is looking into the interplay between NOC placement and memory bandwidth. These are 3 different scenarios. So these 4 boxes, you can say these are these 4 times 4 NOC that you see here on the previous picture. And the question is, if you have all the memory controllers here on the left and all the accesses from the NOC to the CPU and the system level cache, or the slices of the system level cache distributed uniformly, this would be the scenario T1. If you place them differently, you have all system level caches closest to the memory and then all the CPU closest to the center of the chip. Or if you do the opposite way around, these were different possible configurations of the placement in the NOC. They also analyzed what happens if you have about the VNet support. That's what I mentioned, one of the extensions done in the model. The standard GEM5 have only one link, so there's one single link for all the messages transferred through the NOC. But the real hardware is able to have 4 links per signal, and this means you can transfer 4 kinds of messages, so request, response, snoop, and data at the same time through the link. And there is also the possibility to multiply this and to have, for example, double the amount of links for request, response, and data, and leaving only 1 for snoop. So these are different scenarios. And you see here the same scenarios here for the NOC placement, T1, T2, T3. So T1, the one here is the one here. And what is the impact then of having different, or having not at all, or having VNet support? So if you look into the first scenario, which is the most uniformly distributed, if you would not have VNet support, you would end up seeing only half of the bandwidth that you have available on the chip. So it's important you have actually this VNet support also in the simulation and in the hardware in order to reach something like 70 something percent, which is what is normally technically achievable. If you could have the second scenario with this partition, then the dependency between the VNets would be even stronger. And on the third case, it's a little bit similar than on the first, but just not having VNets will let you down to 30-something percent of the memory bandwidth achievable. So this is the kind of studies that GEM5 is able to show you. So how is the interplay of different hardware characteristics impacts then on the performance? A second study that has been done is looking into the NUMA architecture, and also for this, the Gen 5 model was extended to represent whether you could have, for example, on this large chip, 4 NUMA domains, being the NUMA 0, for example, this one here. Just as you see, so this is the same kind of representation I had on the previous slides, but this is zooming in here on the NOC routers and access to memory, and then the core and the SLCs. Interestingly, and you will see this on one of the last slides, this chip has both HBM, has high bandwidth memory, and DDR. So also the support for this hybrid memory configuration was represented on the model. For this, first of all, to implement the NUMA domains, you needed to label each CPU and memory controller with a distinct NUMA identifier, and also assign this system-level cache to the specific memory controllers. And you can then define in the model what is the latency between going from one NUMA domain to another or staying on the same. Yeah, so the hybrid memory models were also included and so on. And the first studies that were done is, okay, let's see at all having NUMA configuration or not NUMA configuration. In this case, or say having one NUMA domain or multiple, looking into just the lower part of the chip, so the 2 quadrants on the bottom, you could organize them in one single NUMA domain, or you could split this in 2. And you look in combination also with the fact whether you have only 1 link per VNet or 2 links per VNet, as shown in the previous slide. What you see is that when you only have 1 link per VNet, the memory bandwidth you achieve, whether you have 1 NUMA domain or 2, is maximum 50%. If you only have one NUMA domain, it's even only 20-something%. So it's important you have the support for VNets, and in this case, you don't see that much of a difference between splitting your domains in 2 NUMA or only having 1. Another thing, looking into the hybrid NUMA architectures, is simulating really the interplay between DDR and HBM, and what is the impact of prefetching. How does it make a difference if you prefetch from DDR or if you prefetch from high bandwidth memory? The design is here on the left, so these blue things are the routers that are then addressed into the high bandwidth memory. The orange ones are those that are addressed into the DDR, and then you have 2 cores per each one of them. There are many different applications have been looked into and benchmarks. This is actually the work from a master student in our team at Jülich. I just showed you here the results for Mini FE, but if you are interested, the full master student master work is here on the link. So this is Mini FE, where you have on the left block no prefetching at all. On the first block, so the so-called aggressive stream prefetcher is also a specific kind of prefetcher implementation that he added to the Gen 5 model. And the last one is timely aware stride prefetcher. And you see if you have all the data in HBM, if you have part of the data in HBM, or if you have everything on DDR. It's clearly a strong difference if you are in DDR or if you are in HBM. And it seems that from those prefetchers, the one with the best performance, the one with lowest here is better, is this aggressive stream prefetcher that kind of tries to get data very quickly from memory. So the conclusion was in this particular case that there are good prefetch opportunities for high bandwidth memory, but their memory contention it's a challenge then for DDR. And the last one I wanted to show is work ongoing by a PhD student in our group, is Fabian, that is looking into the multi-chiplet configuration. So does it make a difference for different parameters, whether your chip is monolithic, just one piece of silicon, or if you have a multi-die design, as for example AMD is doing. So in this case, there are gateways that allow you to communicate between the different chiplets, and then you can configure what is the gateway latency and what is the link latency, and do different studies. And this particular one, which is here in this link, in this publication, looked into the NOC utilization for the monolithic and the multi-die, and you see how much more the NOC is used when you have a multi-die design. And then looking into the attainable bandwidth and the bandwidth you see at the memory controller, these are the values for the monolithic and for the different chiplets configurations with different gateway latencies and link latency. You don't see that much of a difference in between them. So it's interesting to see that this chiplet split doesn't seem to make a strong impact in this particular parameter. Now, looking into the architecture itself, after all these co-design activities and looking in which direction to go, So first of all, the performance targets, and I think I mentioned them already at the beginning, but just to remind, key performance target is data transfer, having a high memory bandwidth with over 1.6 terabytes per second, and for a stream at least 1 terabyte per second. Computational power around a bit higher than 2 teraflop is the target, and then having real application efficiency with the SPIDE per flop ratio around 0.5, 0.4 for maximum or peak, depending what you look into. Based on these targets and all what have been simulated and done in the meantime, these are the key values that came up for the design, and you see on the right an artistic view of the chip itself. And to go a little bit more in the detail, so what you see on the right is a kind of idealized block diagram. So these are 80 Neoverse V1 ARM cores that are the ones here in the middle. They have a nominal frequency of above 2 gigahertz, 2 SVE units, so scalable vector extension units with 256 bits per core, and the cache hierarchy with 64 kilobytes on the L1, 1 megabyte on the L2, and 84 megabytes on the last level cache, or the system level cache. Memory bandwidth, there are 4 blocks of high bandwidth memory, each one of them with 16 gigabits, so in total 64, achieving us or targeting, as I said before, a peak bandwidth of around 1 terabyte per second for stream. The hybrid memory subsystem combines DDR and HBM2. 4 blocks of each side, and then the fabrication is going to be on 6 nanometers from TSMC. The target of power is 400 watt, and the peak performance, as I said already before, is over 2 teraflops per second for double precision. So these are the key parts. I have a backup slide if you're interested on the core of the Neoverse, if you want to look in, but this is also what you can look also on the websites. And just to conclude, because it's already 45 minutes, and I think we need to spare some time for discussion. What has been interesting, at least for me, is to see how complex it is to develop this kind of processors, how difficult it is, how many expertise and dependencies are between all those components, how important it is to have proper modeling and benchmarking tools to really learn and understand what is the performance that you can achieve. And then some important, I find it interesting, so when we have project reviews, so it's always the question, what are really the co-design input you brought and how did this impact the final design? So pinpointing this is extremely difficult because there are so many other factors that play a role and mostly related with cost and with just technical limitations or technical constraints that is very hard to pinpoint it. So if you look into the Gen5 analysis, this was more about giving trends and trying to verify expectations that you might think they make sense from the intuitive perspective, but you still have to have numbers to back them up. So it's difficult to pinpoint down, but there are, I believe, very good opportunities for performance and energy efficiency improvements if we as a community and HPC in general would invest in common tools for data-driven and systematic modeling of this kind of chips. And with this, I'm done, and thank you very much for your attention. I'm open for questions.